Okay, the next topic is uh, the vector identities. We have to prove some of the identities which are very useful. The first identity is curl of grad phi is equal to 0. In the mathematical notation, curl means this is del cross, okay, and grad phi is simply del phi. So del cross del phi is equal to 0. This is what we need to prove. Okay, so first we start with the scalar quantity. All right. So first we define the scalar quantity. Okay, we defined this. Now we will first start defining a scalar quantity, right? So the scalar quantity could be defined in this way. So let phi be the scalar function of the variables x comma y comma z, right? Then what is the grad phi? Grad phi is gradient of this. Gradient is del phi. This is nothing but dou phi by dou x into I cap plus dou phi by dou y into j cap plus dou phi by dou z into k cap. So this is the standard definition of the gradient. Now what I am supposed to do here is we will be taking the curl of this function, correct? So this implies if I want to take the curl of the gradient of the function phi, right, that is equal to del cross of this del phi. So this is equal to, I know that it's a del cross function. Curl means it has to be a determinant. So first we write the determinant and then we'll try to solve the determinant. This is I cap, j cap, k cap. Then this by dou x, dou by dou y, dou by dou z. And below that I need to write the x, y and z components of the grad phi, that is dou phi by dou x, dou phi by dou y, and this is dou phi by dou z, its determinant. Okay, now this means let us try to expand this. So this is equal to, we know that the first term will write that is I cap into, when I write a I cap, this is dou by dou y of the dou phi by dou z minus the dou by dou z of, this is dou phi by dou y. All right, so this whole thing into the I cap. Right now, instead of expanding this further, we can simply write a summation. Summation in the sense you will do the same thing repeatedly. So that is equal to summation. Now you see, I'll apply this dou by dou, which means dou square phi by dou y dou z. partial differentiation twice minus, see this function, this is once again dou square phi by, this is dou y dou z into I cap. So what happens? They are same, they will get cancelled. So 0 into I cap plus next term will also be 0. 0 into j cap plus 0 into k cap. Alright, so when we have that coming up, it's very clear that we are going to get 0 vector. So this is 0 vector, that is the answer. Alright, so we need to remember curl of gradient of a function phi is always 0. I don't have to do that calculation whenever we get such things in our regular problems. Okay, that's why this is a important identity. Right. Then let's go to the next identity, that is divergence of, this is curl of a vector A, this is also equal to 0. So mathematically you can write del dot, this is del cross A vector is equal to 0. Okay, to prove this, we'll start with the vector A now. So let vector A be denoted by, it's a vector, so I need to use the I, j, k and components. A1 into I cap plus A2 j cap plus A3 k cap. All right, this be a vector. Now first is in the given question we need to take the del cross A. So let's write therefore del cross A vector, let's say curl of A is equal to, this is unit vectors I, j, k, dou by dou x, dou by dou y, dou by dou z, and a1, a2, a3, its determinant. So we know that in the short format I can definitely write this as summation of I cap into, this is dou a3 by dou y minus dou a2 divided by, this is dou z. This is my function, this which I am going to expand further. All right, now let's go ahead and do the remaining half. Remaining half in the sense I need to take therefore divergence of this curl A is what? This is equal to del dot, this is del cross A vector, right? So this is equal to, I know that del dot is nothing but this is a summation of dou by dou x, summation of dou by dou x into, so this is summation of dou by dou x into I cap. This has to be applied as a summation. So summation of dou by dou x into I cap. This is my first function. That's a del dot. The del cross A we just have written. That is summation of I cap into, this is dou A3 divided by dou y minus dou A2 by dou z. Okay, this is what we have now. This is from the previous equation. Okay, just now we have written the same thing, right? So that part I'm using here now. Okay, so we get this now. So what I can do, I'll just erase this. So this is a square bracket for that term. Okay, now going ahead. So this is equal to, now let's try to multiply them, right? This implies this is equals to, uh, both are summations over the same term, so you can keep a single summation, okay, of I dot I can multiply. So dou by dou x is getting applied to each and every term, right? So when that happens, this is equal to dou square a3 divided by, because dou by dou x is getting applied to this and this is getting multiplied to the second term. So for both terms we need to multiply. That is dou square a3 by dou x into dou y minus, this is dou square a2 divided by, this is dou x into dou z, dou x into dou z. So this is my term. All right, so the I is gone. I don't have to write I because I dot I is 1. Okay, now let's move on. We will try to write it in the following fashion. So this is equal to, let's try to expand now. So whatever term we have, we should expand. So expanding this term, right, that is equal to, let's expand. So whenever I have a x will be replaced by y will be replaced by z. In each term you expand the summation. So first term, this remains as it is, okay, so that is dou square a3 by, this is dou x dou y, first term, minus the second term is dou square a2 by dou x into dou z. This is the first term. Okay, then plus, let's write a second term where a3 becomes a1, so that is dou square a1 divided by x becomes y becomes z, so this is dou x becomes dou y becomes dou z, minus, same thing, I have a a2 in the term, a2 becomes a3, so this is dou square a3 divided by, this is dou y, dou x dou z, dou the x becomes y and z becomes x, this is dou x. So my term becomes like this is dou x. Then let's write the third term, so plus, in this case the term becomes equals to, so plus, this is uh, dou a1 is there, it becomes a2, dou square a2 divided by dou y dou z is there, so that dou y dou z becomes y becomes z, so this is dou z, z becomes x, dou square this divided by dou z dou x, then minus, there is a3 becomes a1, okay, so dou square a1 divided by, this is, we have a dou z dou x and that dou z dou x becomes equal to, this is dou square of a1 divided by dou z into dou y. So the total terms are going to be like this. We have two terms getting expanded to 6 different terms, what we can see now. Okay, now dou square a3 dou y into dou x, this is dou square a2 divided by dou z dou x minus dou square a1 divided by, this is dou z into dou y. So if you see the terms carefully, I have a dou square a3 by dou x into dou y here. So this term and this term will cancel. Okay, and then dou square a1 is actually here, dou square a1 by dou z dou y. So plus and minus will get cancelled. So this is negative and the other one is positive. So I can observe that the terms are getting cancelled over here like this. This gets cancelled with this and this gets cancelled with this. So they are equal. That's why this becomes equal to 0. Alright. So since the terms get cancelled, we have the whole term becoming equal to 0 here. Okay, let's move on to the third one. Okay, this is divergence of phi into vector A can be substituted as phi into divergence of A vector plus gradient phi dot vector A. So this is the statement written. Now mathematically we can write this as this is del dot phi A is equal to the phi into this is del dot vector A plus this is del phi dot vector A. So either of this can be given as a statement. We can prove this. Okay, so we'll start like this. Let vector A be is equal to A1 into I cap. So we'll write the x component as A1 I cap plus A2 j cap plus A3 into k cap. Right now, also we need a scalar function phi. Okay, and phi be a scalar function. Okay, now so we'll start with the phi into a because that's what is present in the left hand side. So first we start with phi into vector a. This is equal to, I have to perform the phi multiplication with a1 I cap plus a2 j cap plus a3 into k cap. So in short, I can definitely write this equals to summation of phi a1 into I cap. Call this equation number 1. Alright, now what we do in the next step, I am going to perform the divergence of this function. So therefore, divergence of phi a, right? This is equal to, divergence is defined as multiplication by del dot. The del operator should be taken dot product. So del dot of this is phi a. So del dot operator is what? We know that this can be directly substituted as summation dou by dou x, partial differentiation with respect to x, and multiplication by I cap. I should multiply this, take a dot product with the summation from equation 1 I am writing. Just observe, from equation 1, the phi a is nothing but summation of this is phi a1 into I cap. Okay, so I cap terms can be multiplied. So instead of writing two summations, I'll write a single summation. This is equal to summation, right? This is dou by dou x of phi a1. Dou by dou x of phi into a1. Okay, so this means when we write dou by dou x of phi into a1, I can expand this. So this partial differentiation can be applied to both phi and a1 separately by using the product rule. So what is the product rule says? Keep the first function as it is, that is phi. Okay, and differentiate a1, so that is dou a1 divided by dou x, plus keep the second function as it is and differentiate the first function, that is dou phi divided by this is dou x into a1, right? Now this means, now you see that I can keep the phi outside now, so this is equals to, I can write this as, I'll keep the phi outside because summation has nothing to do with the phi. So this is phi into, this is summation dou a1 by dou x, first part, plus, see the second function I'm trying to write it as a different term because I want to get the answer in a different way. Alright, so this is summation, I'll write dou phi by dou x into I cap into summation a1 into I cap. Then only I can do this, right? Because dou phi by dou x into a1 means perform dou phi by dou x into I cap into this, right? Now I can get the answer in the required format. So this is equal to phi into summation of dou phi by dou a1 by dou x is nothing but that is divergence of A. This is divergence of vector A, plus performing of dou phi by dou x into I and taking a summation is nothing but that is gradient, grad phi. Okay, dot the summation of this is nothing but this is vector A itself. So that is the RHS. So we proved that identity like this. Okay, next identity. This is also pretty important. Identity number 4 is about taking a curl. So curl of phi a vector is equal to phi into curl vector A plus this is grad phi cross vector A. Okay, so this is the property. So in mathematical notations, we can definitely write this as del cross phi A is equal to, this is phi into this is del cross A vector plus this is del phi cross vector A. So either of these can be asked in the statement. Okay, so now what we do, we'll directly convert this into the uh, required format. We start from the left hand side and then we get the answer which is present on the right hand side. So we'll start with the definition of phi and a vector. Okay, so that is, let vector A is equal to, this is a1 I cap plus a2 j cap plus a3 into k cap. Alright, so this is the vector and let's define the phi. So phi be a scalar function. Okay, so when we have this, first we need to start with the phi a, right? So this implies the phi into vector A is nothing but the scalar function phi into a1 into I cap plus phi a2 j cap phi a3 k cap. Now in the next step I need to start with the left hand side. So I'll start with the LHS of the given theorem. It says that you need to take the curl of phi into A. So I know that curl is nothing but this is del cross phi a. So how to apply this del cross function? This is equal to, this is I cap, j cap, k cap, apply dou by dou x, dou by dou y, and the dou by dou z. Below that I need to write phi a1, phi a2, phi a3. This determinant I am supposed to take now. Okay, so let's apply this further. So this is equals to summation I cap into, I have to apply dou by dou y. So this is dou by dou y of phi into a3 minus the dou by dou z of phi into a2. So this summation I need to take, in the sense next I need to write minus j into another part plus k cap into the third part. Anyway, let's do it in this fashion. Okay, we'll write a summation so that you don't have to expand this completely. Without even expanding that, we can get the answer. Okay, so that is equal to, I'll write summation I cap into, so we can see that each of the partial derivative is actually being applied to a product. So let me expand this. The first term, dou by dou y of phi into a3, I can write it as, phi is my first function, this is dou a3 by dou y, plus I have to apply the derivative to phi now, so this is dou phi by dou y into a3. This is the first term. Only this is being expanded like this. Only this term I am expanding now, and I got this answer. Okay, then I have a minus sign, and I have to write this partial differentiation in the same way. Keep the first function as it is, differentiate, that is dou a2 by dou z, phi into, this is yeah, so this is dou a2 by dou z, plus next term is keep the differentiation with the phi, so this is dou phi by dou z into a2. Okay, we got this, right? So in the next step I have to simplify this by means of, I keep summation I cap, or let's put this way, this becomes easier now. So if at all I bring the phi inside this, okay, summation of this term I'll bring it inside, so that that can be applied easily to the function. So this is equal to, see the first term, I try to take the summation terms with the function, the functions which have summations I'll try to club them together. Okay, so that is, anyway, I'll write summation I cap into, so I'll write the terms containing phi first, so that is phi dou a3 by dou y minus phi dou a2 by dou z. What I did, I clubbed this term and this term over here. Okay, and the next term I'll write in the very similar fashion, plus the constant I'm going to, these terms have some constant with them, so that is dou phi by dou y a3 minus dou phi by dou z into a2. Okay, so how we are getting that, this is a term, this is a term, clubbing together we get this term. All right, now what I do, I bring the summation inside the brackets, right, and I write the constant. So in the green color terms I can see that the phi is a constant, so I'll take the phi outside. Okay, then I write summation, I apply the same thing, so there is dou a3 by dou y minus dou a2 by dou z into I cap. This had an I with that. Plus, we'll write another summation. Okay, so that is summation of the second term, the yellow colored terms. We'll club them together as follows. This is dou phi by dou y into a3 minus the dou phi by dou z into a2. Again, I need to multiply this with the I cap. Okay, so we do that. After this, now the next term is nothing but, I can try to write it in the following fashion. This is equal to, there is a phi. See, the summation of dou a3 by dou y minus dou a2 by dou z into I is nothing but, this is actually a determinant. This is I cap, j cap, k cap. I have the dou by dou z, dou by dou x, my mistake, dou by dou x, dou by dou y, dou by dou z into the same term. This is a1, a2 and a3. Okay, apply the determinant to this. Now we can see that this is nothing but I cap into dou y by dou y of a3 minus dou by dou z of a2. So that term is there, right? Plus now this part is nothing but, I can write another term, right? So the second term is also going to be a determinant. I'm going to write it this way. This is I cap, j cap, k cap. So instead of this, I had just have a dou phi by dou y. So this means this is dou phi by dou x, this is dou phi by dou y, dou phi by dou z, and we have the terms a1, a2, a3. Just check this now. So I cap into dou by dou y of a3 minus dou phi by dou z of a2. That's what is this term, correct? It means, right, I can definitely write the given term in the form of a determinant, which is nothing but a curl operator. So I can write this as follows. Therefore, this is equal to, so this is phi. So first term is phi, definitely, because I can see that there is a phi outside. So this is equal to phi into whatever is there, I can write that inside the bracket, right, as the del cross vector A, plus the second term is nothing but, you already take a del phi, take a cross product with this A. This is the right hand side of the given theorem. Okay, now let's go to the next theorem. This theorem is stated as follows. So this is del cross A vector is equal to, this is del of del dot A vector minus del square of vector A. Right. So we already start, always we start with the definition. So let vector A be equal to, give the terms a1 I cap plus a2 j cap plus a3 into k cap. Okay, so you start with the curl function, that is del cross A. So what is del cross A? Always we define del cross A in terms of a determinant I, j, k. Dou by dou x, dou by dou y, and dou by dou z. We have a1, a2, a3. This is always equal to summation I cap. I am going to write it in the short format, so that's why I use the summation over here. This is dou a3 by dou y minus dou a2 by dou z. This is the shortest format. Okay, now what we are going to write here is we are going to write this in a different format for our next step. So because it always starts with the left hand side, and it says that I have to perform the del cross del cross A vector, right? That as soon as we see a del cross, that is nothing but a determinant. So we'll write one more determinant now. So I j k, first term is dou by dou x, dou by dou y, dou by dou z. But you see, I have to write the next term, which is the coefficient of I here. So coefficient of I can see that that is equal to dou a3 by dou y minus dou a2 by dou z. This is the first term. Similarly, I need to write the second term. So a3 becomes a1, dou a1 by y becomes z, dou z minus this is a2 becomes a3, dou a3 by z becomes x, dou x. Okay, very similar to this, we'll write the last term. A1 becomes a2, so dou a2 by z becomes x, dou x minus there is a3, a3 becomes a1, so dou a1 divided by this is x becoming y, dou y. Take the determinant of this term. This is what we need now. Okay, so therefore this is equal to, I'm going to use the same short notation. We'll use a summation to write this term. So this is equal to summation. First term will be always a multiplier of I cap into, right? So I am performing dou y of my first term, that is dou y of, what is the first term? First term is dou a2 by dou x minus dou a1 by dou y, right? Minus perform dou by dou z of, this is the second column element, that is dou a1, sorry, dou a1 by dou z minus this is dou a3 by dou x. I need to take the summation in this bracket. Let us expand the terms now, just to make sure that we'll be able to understand what exactly we are going to do now. So this is equal to summation I cap into, I'll apply the partial derivative to each of the terms. So first term becomes dou square a2 divided by dou x dou y minus this is dou square a1 divided by dou y square. Alright, then minus this is dou square a1 by dou z square, minus of minus becomes plus, this is dou square a3 divided by dou x dou z. Okay, now what I do, I bring the summation inside the bracket and I rearrange the terms. So when I try to rearrange, what I do, first I write the summation of I cap into, see the terms which I'm going to club now. I'll write dou square a2 by dou x dou y plus dou square a3 by dou x dou z. Okay, this is nothing but I'm clubbing this as this. Okay, that's my first term, right? Then I'll take a minus outside. Okay, let me close this bracket. I want to apply different summations. So this is summation over I cap into, we'll write another term now. Okay, that is, since the minus have gone out, I can simply write this as dou square a1 by dou y square plus dou square a1 by dou z square. Okay, now what we try to do here is we'll try to expand the terms in the following notation. right? So we'll try to add and subtract one term to this above. So I'll write what I'm going to do now, but before that let me show the coloring that's happening. These two, we get this, okay, we club them to get this. Okay, fine. Now uh, so this is equal to, what I'm going to do now is we try to add and subtract the same term, that is adding and subtracting the term, that is summation I cap into, this is dou square a1 by dou x square, because I don't have the term like dou square a1 by dou x square in this, right? I have with y square and z square, I have the term inside the yellow color. So in order to bring it, I'll add that and I also subtract that. Okay, so that means this is what is going to happen. Summation, first term is summation I cap into, I do the addition to this term. The addition in the sense, this is dou square a1 by dou x square. I'm adding the term to this first term, that is plus remaining two terms. I'll write them as it is. Okay, so that is dou square a2 by dou x dou y plus dou square a3 by dou z dou x is the first term. Then minus, right? After now I need to subtract. So this is minus summation I cap. So it's actually, since the sign is minus, it can be considered as I am subtracting this term from the given this thing. Okay, so I can write this as minus, so this is dou square a1 by dou x square plus dou square a1 by dou y square plus dou square a1 by dou z square. This is done. Now I will show you the previously present terms. So you can see that these are the two terms which are already there. Okay, and then these are the two terms which already we have. Now I use a different color to note that where I added and where I am subtracting. Okay, so you can see this term is actually getting added here and getting subtracted here. So because the sign is minus, right? So that's why it is getting subtracted. So adding and subtracting makes the terms look like this. All right, so once this is done, in the next step, okay, let's do this this way so that this becomes easier for us. I'll try to take a dou by dou term outside, that is equal to, see, this is summation I cap as it is. Then I try to take a dou by dou x outside the first term, because you can see the, when I take it out, this is dou a1 by dou x, one of the dou by dou x has gone out. This has dou by uh, dou a2 by dou y plus dou a3 by dou z. This is what I have, minus summation. Okay, this is how it looks like. So if a1 is common for all of them, so I'll write it as dou square by dou x square, dou square by dou y square plus dou square by dou z square. A1 is gone out, a1 is this, into I cap. Okay, now let me write it in a slightly modified way. This is equal to summation, what this, there is a dou by dou x, I will move it to the rightmost side, so I'm going to write this as dou by dou x of, what is inside the bracket is nothing but this is divergence of u, right? This is divergence of vector a, okay, into I cap, minus, there is a summation, uh, summation of dou square by dou x square, dou square by dou y square plus dou square by dou z square is nothing but it is a double differential operator. del square, and there is a summation a1 into a cap. This is nothing but I'll first write in the words. This is gradient of divergence of vector A minus this is del square of vector A, del square of vector A vector. So I can write this as, therefore this is equal to, already we have written this in this format, this is del of del dot A, sorry, it's not a cross product, it is a dot product. Allow me to correct. This is del dot right, this is sorry, okay. This is del dot A minus del square vector A. This is the RHS. This itself is the right hand side of the given uh, okay, is RHS. Okay, right. So that is an important theorem to prove. Okay, let's go to the few problems based on our theorems that we have used so far. Okay, so this is the question: if u and v are scalar functions, if they are scalar functions, then show that this is del dot u into gradient of v minus v into del u is equal to, this is u into del square v minus this is v into del square u. Okay, so what we do, we use the one of the vector identity which we have used. So I'll write that itself. So we know that that is del dot of, if I try to write this as phi into a vector, this is equal to phi into del dot a vector plus this is del phi dot a vector. This is the third identity which we saw today. So I am applying that to prove this given question. So what I do here in this case, so take the phi equals to u, and there is a v now, so v is nothing but it, I'll apply a vector as del v. So v is a scalar but del v is a vector, right? So this implies, right, we start from we apply this in the above equation, so that makes it like del dot, this is u into delta v is equal to, this is u into, right, this is I'll use a bracket, del dot the second function which is del v, okay, that is the first term, plus del phi becomes del u dot del v. So I can write this as this is equal to u times del dot del v is del square v plus this is del u del v. Right now this is the first part. I'll call this is equation 1. Now without doing the calculation once again, I can write similarly. I can try to write this as del dot v times delta u. V times del u is equal to, I can rewrite the function in a very similar fashion like equation 1. So that is v times del square u plus this is del v into del u. This is equation number 2. Now you look at the given statement left hand side, that is actually I have to have a subtraction. So that is something minus this. So that can be obtained by performing 1 minus 2. Equation 1 minus equation 2. Let's do that. Therefore, equation 1 minus equation number 2 is going to give right here. So this is equation 1 minus equation 2. This gives the following cases, right? That is del dot u dot del v minus this is del dot v into del u. V into del u. Okay, this is the left hand side is equal to, on the right hand side I can see that the del u into del v get cancelled. So this is u into del square v minus v into del square u. So on the left hand side I can actually move the del outside. So this is del dot, this is u into del v minus v into del u is equal to, we can write this as u times del square v minus v times del square u. This is what they had asked us to prove.